Hello, my name is Anirudh Konidala, and today we're going to be talking about virtual memory. Take a look at this cow. If you've used Linux before or you're very fond of the command line, you've probably heard of the command line tool cowsay. Cowsay is just a simple way where you can have a cow, an ASCII cow, output any text you want. And I thought this cow was very important because it's basically the synopsis of how every program on your machine is running right now. Every program on your computer genuinely believes it owns all of memory. Chrome thinks that. Your terminal thinks that. Even the tiny program that you write in your CS340 homework thinks that. They're all wrong, and your OS engineered it that way on purpose. Here's why that matters though. Your laptop has 16 gigabytes of RAM, for example. Open Chrome, open VS Code, and Slack. And then you've realized you've burnt most of your RAM before writing a single line of code. Now imagine two programs accidentally sharing the same memory address. One writes and then one reads. This is an example of corrupted data, which is a crash. In the worst case scenario, that is a security hole. So how does your OS let hundreds of processes run safely on fixed hardware? The answer is simple and actually brilliant. Give every process its own private view of memory. For example, let process A think it owns address 0x4000, and then let process B also think the exact same thing. And here's the key about both of those processes. They're both right, because those are virtual addresses. Fiction. The OS maintains a transition layer that maps each process's virtual addresses to completely different physical locations in RAM. Neither process ever knows that the other exists. Think of a hotel where every guest keycard says room 101. Alice is on floor 2, while Bob is on floor 5. They never collide because the front desk translates the keycard to the real room on every visit. That front desk is the MMU, the Memory Management Unit, and it's a piece of hardware that intercepts every single memory access your program makes and resolves the real physical location. This happens billions of times per second, invisibly. RAM is divided into fixed 4 kilobyte chunks called pages. Every process has a page table, a private map of its virtual pages to physical frames in RAM. Did you happen to miss a page? The hardware fires a page fault. The OS then loads it from disk, and the execution resumes. Your program never knew it happened. First, isolation. Process A cannot touch process B's memory. That's why it matters. This is the foundation of OS security. And here's the one that surprises people. When you call malloc, you don't actually get RAM. You get virtual address space. Physical memory only gets allocated the moment you actually touch it. Everything you've written in this course in CS340, including malloc, fork, and shared libraries, all run on top of this abstraction. Virtual memory is the OS's greatest magic trick. It lies within every process, tells each one it owns the whole machine, and then quietly makes it true. That's the design behind virtual memory. Thank you.